Okay, in this lecture, we will be covering the concept of implicit differentiation. Sometimes when you have an expression in both x and y, you may have implicitly defined one or more functional relationships between x and y. We're used to this. We're used to often seeing questions where you have things like y equals f of x. Y can be explicitly written as a function of x. But that's not always the case that you can solve for y explicitly in terms of x. You may not be able to solve for y. You may not be able to solve for x, but you still will have one or more functions, say y as a function of x, defined by your expression. So, as an example, here we have the classic x squared plus y squared equals 100, and we know that this, if we graph it, gives us a circle of radius 10, centered at the origin. If we were to decide what are the functions determined here, and we looked at, say, functions of x, well, this graph does not pass the vertical line test. This is not the graph of a function. But if we say restrict ourselves to the top half of this graph, that would be the function y equals the positive square root of 100 minus x squared. If we were to then look at the bottom part of the graph, then this would be the function y equals negative root 100 minus x squared. So what we see here is that this expression implicitly defines two functions. Where we can get y as a function of x. Now, we haven't talked about differentiation yet, but the idea here is, in this case, even though we could actually break this into two functions and solve for y in terms of x, you don't have to do that in order to find dy dx. If you want to find the derivative, dy dx, we can implicitly differentiate this left-hand side. So we'll look at an example how to do this now, and then we'll explicitly describe the procedure in the next slide. And so what we do is we assume that we can write y as a function of x. So that's going to be very important. And we differentiate both sides with respect to x. So the derivative with respect to x of x squared plus y squared is the derivative with respect to x of 100. And we go, of course, term by term. The derivative with respect to x of x squared is 2x. Now the derivative of y squared with respect to x, we have to think of y, again, as a function of x. So we're going to need chain rule. So maybe we can be careful here. The derivative with respect to x of y squared, and we'll show it explicitly in the next step, the derivative with respect to x of 100, 100 is just a constant, so we have 0. So this becomes 2x plus, and our chain rule says, we take the derivative of this y squared with respect to y times dy dx. The derivative of y squared with respect to y is, of course, 2y. And now, with this expression, notice that we can algebraically solve for dy dx. So this tells us 2y dy dx equals minus 2x, and divide both sides by 2y, and we get dy dx is minus x over y. So this, remember what this derivative represents with the graph. It represents the slope of the tangent line at any point. So for instance, if you want the slope of the tangent line, at any point on this curve. So why don't we say you want the slope of the tangent line when, let's see, why don't we say, we can see something, why don't we just say something simple at the point 0, 10, so that would be here. Well, we know from the picture that the tangent line is horizontal, and we see that dy dx at that point 0, 10, we plug in directly, we have a minus 0 in the numerator over 10, or 0, and we see, in fact, that we did get a 0 slope for that tangent line. And this would hold at any point along the circle. You just plug in the xy coordinates here. So this is the idea. This is an example of using implicit differentiation. To explain it thoroughly, we use the following procedure. So if you're given an expression in f and y, you're given an expression in x and y, call it capital F of xy equals 0. So this capital F of xy just means some algebraic expression, or any mathematical expression in x and y. And then we're going to assume that y is a function of x. Maybe there may be multiple functions in there, y being defined as a function of x. And we differentiate both sides of the expression with respect to x using our chain rule and other rules of differentiation. And then when we're done, we solve for dy dx. So this really is just a formal description of the procedure that we just implemented. So let's do a couple more examples and see this in action some more. So suppose we have this y squared equals x minus 1 over x plus 1, and we want to find dy dx. Well, same thing. Differentiate both sides with respect to x. And again, on the left here, we need to do chain rule. So you don't necessarily have to, again, as I often do with these types of chain rule questions, you don't necessarily have to write the steps I'm about to write for the left-hand side. But I like to do this to make it clear how we are applying our chain rule. So we have the derivative of y squared, again, dy, times dy dx. So that's how we get the derivative of this y squared function with respect to x. Again, always remember, we're assuming y is a function of x. Okay, that gives us the left. On the right, we're going to need our quotient rule. So we need denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. The numerator, we have x plus 1. And then when we distribute this minus 1, we get minus x plus 1 over x plus 1 squared. The x's cancel, and we get 2 over x plus 1 quantity squared. And of course, what we now do is we concentrate on this left side of the equation and this right side of the equation. The derivative of y squared dy, that's a chain power rule problem, so that's 2y times dy dx equals that right-hand side, 2 over quantity x plus 1 squared. And now we solve for dy dx. So we get, divide both sides by 2, and these 2's will cancel. And so we get dy dx is 2 over, and it looks like we have to divide both sides by y. 2 over y times x plus 1 squared. So any time for any combinations of x and y where this is defined, specifically we can't have zeros in the denominator. So x equals minus 1 doesn't work, y equals 0 doesn't work. But aside from those values, we will have this giving us the slope of the tangent line to the curve, to the graph of this function. Let's do another example. Suppose we have the expression given here, and we're asked to find the tangent line at this point 2, 3. So again, proceed by implicit differentiation. Differentiate both sides with respect to x on the left here. With respect to x, the derivative of x squared is 2x. But now we have x times y, and we should note that that is a product rule problem. Remember, we're assuming y is a function of x. So for our product rule, we have first times the derivative of the second, derivative of y with respect to x, that's dy dx, plus the second, y, times the derivative of the first, which is 1. And again, this was product rule on that xy term. Then for the next term, we have minus, and maybe we can write it like this, derivative with respect to x of y squared. And then on the right, the derivative with respect to 1 of, derivative of 1 with respect to x is just 0. This term here, as before, we have a chain rule problem, so the derivative of the outer function, 2y to the 1, times the derivative of the inner function, dy dx. Now we have an expression that involves dy dx, and we need to solve for it. So we have 2x plus, let's group our dy dx terms together. We have x times dy dx minus 2y times dy dx. So we have plus x minus 2y quantity times dy dx. What's left? We have a plus y equals 0. And again, now our goal is to solve for dy dx. So we have quantity x minus 2y times dy dx equals negative 2x plus y, or dy dx equals negative quantity 2x plus y over x minus 2y. So we have now dy dx, but remember that we were asked a question. We were asked, what's an equation of the tangent line at the point 2, 3? Well, first of all, we know we need a point on the line. We're given that. And then we also need the slope of the tangent line. And we know we can get that from dy dx. So dy dx at the point 2, 3, we plug 2, 3 in here. And so we get negative of 2 times 2 plus 3. So again, plugging in 2 for x and 3 for y. And then in the denominator, we get 2 minus 2 times 3. And this will be what? Minus, in the top, we have 4 plus 3 is 7. And in the bottom, we have 2 minus, this is 6. So 2 minus 6 is minus 4, or 7 over 4. And this means our tangent line can be written using our y minus y naught is m times quantity x minus x naught. Our point is 2, 3. So y minus 3 is 7 over 4 times x minus 2. And that gives us our equation for the tangent line at the point 2, 3. We can also, let's do another example here. Suppose we have the following example. Suppose we have x plus tangent of xy equals 0. And we want to again find dy dx, a little different because we now have a trig function involved. But it's the same approach. Derivative with respect to x of both sides. And here we know we can go term by term. So the derivative with respect to x of x is 1. Now this next term we will need chain rule. So we have the derivative of the outer function, leave the inner function alone, and remember the derivative of tangent is secant squared. So secant squared xy times the derivative of the inner function with respect to x. Inner function is xy. And of course on the right, the derivative with respect to x of 0 is just 0. And so now we have this derivative of xy to deal with. So this becomes 1 plus secant squared xy. And as in the earlier example, we now have a product rule question. So the product rule for this question, we have first times the derivative of the second, derivative of y in this case, dy dx, plus the second, y, times the derivative of the first with respect to x, and the derivative of x is just 1, equals 0. So this simplifies to 1 plus remember we want to solve for dy dx. So the first term we have x secant squared xy dy dx plus, and then we have y times secant squared xy equals 0. And we now solve for this dy dx term. So we have x times secant squared xy dy dx equals negative of 1 plus y times secant squared xy equals 0, and divide both sides by this x secant squared xy term, and we get dy dx equals negative, again, quantity 1 plus y times secant squared xy over x times secant squared xy. And that gives us our dy dx answer. So again, these questions all have the same approach where you take your expression and you differentiate both sides with respect to x, but you are using the chain rule, keeping in mind that you're assuming that y is written as a function of x. Another application of this is that we can use it to compute higher derivatives. So for instance, let's find the second derivative of y with respect to x. In order to do that, we start out finding the first derivative. So we have the derivative of each side with respect to x. And so we go through here. Remember, y is a function of x. So chain rule says the derivative with respect to x of y squared will be 2y times dy dx. The derivative of 3x with respect to x is 3. On this side, the derivative of 5 with respect to x is 0. And the derivative of 4y, well, we keep the 4, and the derivative of y with respect to x is dy dx. Now, we can then solve for dy dx. So we have, right, if we bring the 3 over to the left and the 4 dy dx, or the 3 over to the right and the 4 dy dx over to the left, then we have 2y times dy dx minus 4 times dy dx equals negative 3. Here we factor out the 2y minus 4 and divide both sides by it, and we get dy dx is minus 3 over 2y minus 4. Now, given this, we can now calculate the second derivative of y with respect to x. So, right here we have the first derivative. And you can go, you can start from here. This would be a quotient rule problem, or we can start from here. Either way. I prefer to deal with expressions that are linear combinations like this. So let's now differentiate, why don't we call it expression star? Again, with respect to x. So we have the derivative with respect to x of 2y times dy dx plus 3 equals the derivative with respect to x of 4 times dy dx. And we do the same kind of thing. We go through and differentiate each term. So the first term, this is a product. So here, we need our product rule. So the first times the derivative of the second with respect to x. Well, the derivative of the derivative is the second derivative. So we get d squared y dx squared plus the second dy dx times the derivative of the first with respect to x. Well, the derivative of 2y with respect to x is 2 dy dx. The derivative of 3 with respect to x is 0. Then on the right-hand side, we have 4. So that is a constant that sticks around. And then we have the derivative of the derivative, which again is the second derivative. Now, we solve for that second derivative. So bring this purple term to the left and the second orange term to the right. And we have 2y times the second derivative minus 4 times the second derivative equals negative 2 times that first derivative squared. On the left, we can factor out our 2y minus 4 and divide both sides by it. So we get the second derivative of y with respect to x is, we have negative 2 over, again, we're dividing by 2y minus 4, times dy dx squared. But we already solved for dy dx. We have it right here, which means we can plug this in. So this becomes minus 2 over 2y minus 4 times that derivative that we already solved for, minus 3 over 2y minus 4 squared. And that gives us our second derivative. So the principle, the approach is the same. It's just that when you do a second derivative calculation, you have some of your first derivative terms hanging around. And those are also functions of x. So this is the idea. It's good to get practiced with this because we will use it quite a bit when we get into the use of the types of related rate problems that we get into, a very common application of implicit differentiation. And that will be coming soon.